This is the 2019 Higher Level Technical Graphics Question 4, looking at solids in contact and developments. Having a look at the question, the elevation and plan of a sand bucket and beach ball are shown. A 3D graphic of the bucket and ball is also shown. The bucket and ball consists of a truncated inverted cone A and a sphere B respectively. The sphere rests on the horizontal plane as in contact with the truncated cone. The bucket has a semicircular handle S positioned as shown in plan and elevation. Part A, draw the given elevation and plan showing all constructions and points of contact. Part B is to draw the development of the conical surface A, and Part C is to draw the development of the semicircular handle S. Now a few things to watch out for here. Obviously we're going to have a cone and a sphere in contact with each other, so we're going to have some work to do on that. The handle is a slightly different one than what we've seen in questions before. So if it's semicircular, but with the orientation that we're looking at it, that's going to be based on an ellipse. So we'll be able to draw that handily enough, and then we'll be able to develop that as well in the normal way we might develop a cylinder. So setting up our question, we're only asked to draw the elevation and plan. We don't need an end view. So we are going to start by setting up the cone, the inverted cone. So I'm going to draw the central axis for the cone first, the inverted cone, and that has a height of 70. Mark that up. And a radius for the base of the cone is 35. So that's going to be 70 across the top. We are not given a diameter for where the cone intersects here, but we are given the angle, the base angle of the cone. So from there we can work out what it is going to be. So measuring our 75 degrees. Measured from the horizontal, marking 75 degrees here and 75 degrees on this side also. So that also gives us the base diameter of where the cone intersects with the horizontal plane, the ground. So that's going to be this diameter down here, so we'll be able to use that to locate that in a while. Next, I'm going to draw the plan of this, which is going to be a radius. So picking just a random point down here, that can be the center of the cone, and it is a radius 35. And I'm going to bring the distance for this down into the plan. So that point there will give me the diameter for the where the cone intersects with the ground. The circle that's formed from that. So there we have the elevation and plan of the bucket, and I'm just going to put in the handle in plan. We'll look at putting it in the elevation later on. So I have bucket in elevation and the bucket in plan, and we'll put the top onto this there now in a moment. So for our handle up on top, we're told that it's semicircular, which means that the very top of this is going to be equal to the radius of this. So how high up this goes, if we were looking in at the bucket this way, we would see it as a semicircle. So from here to here is radius 35, up to the point on the top would be 35. So up here is going to be up 35 millimeters. So that's the top point, and it is also the end of the major axis. To find the minor axis, we're going to project our 2 points, each end of it up here. So this gives us the end of the minor axis here and here. And now we can use whatever method we like to draw the ellipse. I'm going to use the auxiliary circles method. You could also use the Trammell method, that'll work in this case also. So this is a point on the curve, this is a point on the curve, and this here is also a point on the curve. So the rule is anywhere one of our lines coming from the center here intersects the major auxiliary circle or minor auxiliary circle, you go perpendicular to the axis for that circle. So in this case here, the line cuts the major auxiliary circle. So we're going to go back in perpendicular to the major axis. That same line cuts the minor auxiliary circle here, so our minor axis is down here. So perpendicular to that is coming this way, giving me that point. Same for this one here, minor auxiliary circle, so perpendicular to the minor axis, perpendicular to the major axis. That plots a number of points on our curve, and we can now draw in the handle. And that is the elliptical handle at the top. So that completes our bucket. We have the truncated cone drawn, we have the handle drawn in both the elevation and the plan. For the next part of this video, we need to look at finding the ball, the sphere in position. Now we're told that it's radius 30, so it's going to fit down here somewhere. And we need to locate its position. So we know it's centered somewhere along here, but we don't know exactly where, because we'll need to see where it's going to touch off inside here. Now we can't see that in this view, so what we're going to have to do is we're going to have to draw a sphere that is going to be in contact with the ground and in contact with this up here. So we're going to draw a generic one first, one that's not in the correct position but that is in contact with this here. So if we were told that it's radius 30, I'm going to draw a line that is of 30 millimeters above the ground line, above the XY line. And everywhere along that line, I could position a sphere that is would be in contact with the ground. That's radius 30 in contact with the ground. I can do the same thing measuring out from the side of the cone. So if I take a line out perpendicular to the edge of the cone and mark 30 degrees on it, or 30 millimeters on it, I can measure from taking a line parallel everywhere on this line here now is 30 millimeters from here, and I could draw another sphere, a circle, from any point along that line that is radius 30, and it will touch off the side of the cone. Where my two lines cross at this point here, I can draw a line, draw a circle, draw a sphere that will touch off the side of the cone and off the XY line. So next, just going to set my compass to 30 millimeters. I like to mark it on the page first and then copy it, because then I know that it is the correct distance and it's not springing back in. So drawing that in now. Now this is just drawn lightly as it's not the sphere in the correct position. We're just finding a center of a sphere that touches off the ground and off the side of the cone. I'm going to move that center, locate that center now, that same center down in plan. And it's going to be off out here to the side. So this is that center. The reason it's in this line here is because when we're looking in at the front of it, where the only place we can see where it's touching off the side of it is going to be in line with the center of the cone. So I can take that distance now. I'm going to rotate that around the side of the cone into this position down here, and this is the center that I'm looking for that cone, for that sphere. Reason being, it's in the correct line coming down along this way, and it is also this correct distance out from the edge of the cone so that it's in contact with it and it's not cutting through it. So using that radius 30, again, down here I can draw a sphere in the correct position. It's hidden detail for a bit of it. And that is the sphere in the correct position in plan. Also need to locate this point up in the elevation, but just a quick recap on what we did here. So we've drawn the sphere in the correct, in a position where we can see that it's in contact with the edge of the cone and in contact with the ground. We located the center of that down in plan, and then we have rotated that around the cone until it's in its correct position for what the drawing requires. It's still in contact with the edge of the cone, still in contact with the ground, and also now in the correct position for this question. Locating that up in elevation, so the center is going to be directly above where it is in plan, and the center has to stay at the same height. So if the center is to change height, so if it's to get higher or lower, it'll no longer be in contact with the ground. So the height, the center point, is the same here, so it's just at the same height as it was previously. So we can draw this in the sphere. So this is solid line the whole way around, because it's in front of the bucket, and because it's in front of the bucket is now partially hidden detail. Just going to rub out a small bit of those lines just to make it hidden detail, and that is the sphere in the correct position. So we've got the sphere in the correct position in elevation and plan. So the only part left to do now in all of this is to locate the points of contact shown. So we need to find the point of contact between the sphere and the ball, or the sphere and the cone, and to do that we need to do it in the elevation, in the original elevation that we've drawn. So this is the side of the cone. To find the point of contact between that and the first sphere that we drew, we need to take a line from the center perpendicular to the side of the cone. That gives me this point here. That's the point of contact for the sphere that's drawn off out to the side. It's not for the final position, but it's for the first sphere that we drew. Locating that same point now down in plan, and it's going to be on this line joining center to center. So the point of contact is always going to be on a line joining the axis to the center, the axis of a cone to the center of a sphere, because it's the shortest distance between them. So that's this point. So we're going to rotate that now around onto the correct line joining from the axis to the center. This one. This is the point of contact that I'm looking for. Label it POC. And I'm going to do the same thing now up in the elevation, projecting that back up here. But the question is, where is it up here? Do we extend the line from here on? No, we're not going to do that. It's going to be at the same height. So the height is not going to change. All that has happened is it has moved from this position around to this position. So the height is going to stay the same. So projecting our original point of contact back in, this is point of contact. So that's part A of the question done. Let's have a look at the question now again. Part B is to draw the development of the conical surface A. So we're going to do that next. So for our conical surface A, we need to find the length of the side of the cone. So what would be the true length of one of the sides? This is a true length of one of the sides, however it's not the full distance that we need. We need to find the apex of the cone, because that's the point for all cones that we would develop around, swing around. So I'm going to extend the side of this cone down, crosses down here somewhere. You could do it from the same side also, they'll meet at the same point on our axis. So what we're going to do is I'm going to measure this distance. Just going to pick a point up here to swing around. Measure distance from here up to the end. I'm going to swing around that. So I'm just going to pick a point here to start with. So this line here will be the one that I'll use to start. Now, as this is a truncated cone, we only need to include this part of it, but we still need to find out how far that part is away from the apex. So to do that, again, we're using a true length. So we can see the true length of that off over here on the side. So distance from the apex to that point on the side. And I can draw in this arc. So this much here is that part of the cone. Now we just need to figure out how long the thing is. To do that, we're going to divide the cone up in plan with our 60-30 degree set square and take approximations for the length sides, the side length. So divide it up 60-30. And that breaks my cone up into 12 parts. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Each of those 12 sections are the same size. They're each 30 degrees apart. So what I can do is I can measure the distance from 1 to 2 or 2 to 3 or 3 to 4. It doesn't matter. And I'm going to copy that distance out 12 times. So this is 1 to 2 to 3, 4. So 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11, and 12. Now that's 12, but 12 from 1 to 12 only takes me as far as this point here. I need to go back to 1, so I need an extra point here, and that's going to see that out for me. So if I just label this is 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, and then back to 1 again. You have to go back to the first point again. I can join this up here, and I can darken in my arcs. So there we have the development of the conical surface A. Just a few important things to watch out for. The distance that we swing has to be a true length coming from the apex of the cone down to the base. From the apex down to the top part where it's cut. Okay, so pick a point for your apex and you're going to swing that distance there. Now the final part of this question is to draw the development of the semicircular handle S, which sounds more complicated than it actually is. So first off, what we're going to do is I'm going to draw the semicircular handle S in a view where I can see it looking straight in. So we've already determined that this distance here is 35, so it has a radius of 35. So that is the semicircle S, the handle for S. What I need to do now is I'm going to divide this up with the 60-30 degree set square. Same way that I divided up the cone. And this gives me 6 equal sections, or 7 points on the curve. What I'm going to do now is I'm going to, through point 4, or it can be any point, I'm going to measure the distance from 1 to 2, 2 to 3, 3 to 4. They're all the same anyway. So 1 to 2, I'm going to copy that from point 4, so that's point 3 there, point 2, point 1. Same on the opposite side, point 5, point 6, point 7. So the development of the semicircle is this line here. So all that I've taken is I've measured the distances from 4 to 3, swung that up here, from 3 to 2, added that onto it, from 2 to 1, added that on. Same on the opposite side, from 4 to 5, added, measured that here, from 5 to 6, added that on, and from 6 to 7, added that on also. So that completes the development of part C. So this also completes the question. It is the 2019 higher level question 4.